There are some very common linear transformations in low-dimensional spaces. Here I'm talking about R2 and R3 in particular. That it's really handy to know what the matrices for these transformations are. So when I say geometric transformations, what I'm talking about are transformations that we describe not in terms of not in terms of a matrix, but just in terms of geometrically what happens to the vectors. So in particular, let's look at some examples. Maybe the main one is reflection across an axis. So we can, of course, there are two axes in R2, so we can, there are two different flavors for this kind of linear transformation, and we can figure out a matrix for each of them just by seeing what they do to the standard basis vectors in R2. So the standard basis vectors in R2 are these two. There's the vector 1, 0 that points in the x direction, and then there's 0, 1 that points in the y direction. Right? So this we would call E1, and this we would usually call E2. So let's see what happens when we reflect across the x-axis. So when we reflect across the x-axis, the vector that was I'm sorry, that's backwards. When we reflect across the x-axis, the vector that's pointing in the x direction actually stays put, but the vector that was pointing in the y direction gets sent to its negative, like this. So this result is 1, 0, and this result is 0, minus 1, right? But we've seen that if you want a matrix to represent a linear transformation, all you need to do is take the action of that linear transformation on the standard basis vector, take the results, and sort of put them all together into a matrix as columns. So this will give us the matrix whose first column is the first output, which is 1, 0, and whose second column is the second output, which is 0, minus 1. So this matrix represents reflection across the x-axis. Okay. Maybe one word on why this geometric operation actually is a linear transformation. Remember, a linear transformation has to preserve vector sums and scalar products. That is to say, the transform applied to a sum of vectors has to be the same as the sum of the transform of the two vectors individually. So suppose we had any two vectors in R2 here, say these two. Their sum in this case is going to be, right, something like this. Okay. Well, if you reflect those two, right, across the x-axis, you get something like this. And then if you add the sum, you get that. But this blue vector is exactly the reflection of that blue vector. Or it would be if I drew it perfectly, which I didn't do. So this reflection operation clearly preserves the vector sum. Right? You could either add the vectors and then do the transform, or do the transform and then add the vectors. You get the same thing either way. And that means that this really is a linear transformation. And so we're justified in just taking these two output vectors and putting them together into a matrix. If we do the same thing for reflection across the y-axis, so reflection across the y-axis, that's really reflection in the x direction, right? And that's just going to give us minus 1, 1 on the diagonal like this. Notice that how we can get a matrix for reflection is we take the identity matrix, but we just put a minus on the 1 that sort of corresponds to the variable that's being flipped, or the direction that's being flipped. So here we reflected across the y-axis. That means this first one was reflection across the x-axis. That means it's the y direction that's being flipped. And here's a minus 1 on the second one, which is right in the y position, really. Right? These are, I guess, this is the x position, this is the y position. And when we reflect across it, the y-axis, it's the x direction that's being flipped, and so there's a minus on the first position. All right, another really common geometric operation is rotation. And rotation definitely is a linear transformation. If you have two vectors, like this. Their sum is going to be something like this. So what happens if you rotate by some amount? Let's say rotate by an angle theta. Well, that's going to make it something like this, right? But since all of these vectors are being rotated the same amount, the sum of the vectors before and after you rotate, right? The rotation of the sum is the same as the sum of the two rotations. So this is a linear transformation. So we should be able to find a matrix for it, and we'll do it the same way. We'll just apply this transformation to this two standard basis vectors. So let's see, if we take E1, which again is 1, 0, what happens to that when you rotate by an angle theta? So right, normally so if we rotate this vector by an angle theta, right, it's going to be like this. So here's theta, there's the x-axis, here's the y-axis. We need to figure out what are the coordinates of this vector. Well, the length of this vector has to be 1 because rotation doesn't change lengths. So like this. But if you have, right, we have this right triangle here and the hypotenuse is 1, but that means that the vertical side has length sine theta and the horizontal side has length cosine theta. But that means that this vector is the vector whose x-coordinate is cosine theta and whose y-coordinate is sine theta. Okay, so that's the result of applying this rotation operation to the first standard basis vector. Now let's do the same thing with the second standard basis vector, 0, 1. When we rotate that, it's like this, okay, and the angle theta shows up right here. Well, again, we have a right triangle with hypotenuse 1, but this time the sine of this angle theta actually shows up at the top of this right triangle. And it's going sort of in the negative direction. So this is negative sine theta, and that's an x-coordinate, not a y-coordinate. So for this vector, the x-coordinate is minus sine theta. And the y-coordinate, that's this blue distance here, that's the cosine of theta since it's adjacent to the angle. So that means the y-coordinate is cosine theta. All right, and then as usual, we can get a matrix for this transformation just by putting these two output vectors together into a matrix. So that's going to give us cosine theta minus sine theta, cosine theta. So this matrix represents rotation about the origin by an angle theta. The nice thing about this matrix is theta can be any angle at all. It can be negative. It can be bigger than 2 pi. It doesn't really matter. This matrix always gives you rotation about the origin by the angle theta. There's one more geometric operation that maybe isn't as common, but turns out to be very useful nevertheless, and it's called shearing. So shearing is it's easier to describe in pictures than in words, so let me just draw a picture. So if we have our standard basis vector, I'm going to call this operation shearing in the y direction, so shearing the x-axis in the y direction by some factor, let's call it c. And what this does is it takes the standard basis vector in this direction, so the standard basis vector that points in the x direction, and it adds to it some vector in the y direction, but a vector that's length c. So what we're going to do is the y basis vector we're leaving alone. Okay, so this was 0, 1, and we're sending it to 0, 1. And the basis vector in the x direction, we're going to add c times the basis vector in the y direction. So, right, it was here, but now we're adding this vector, which is c times 0, 1, and that gives us this vector here. So this was 1, 0, but we're adding c times 0, 1, so this produces the vector 1c. Okay. Now the geometric effect here, so if we draw the full coordinate system with the x-axis and the y-axis, the geometric effect of this linear transformation is sort of to scissor the coordinate axes together. It sort of tips the x-axis towards the y-axis by an amount that depends on the value of c here. Right? So if we go over 1, then it tips it up c, like this. So this is shearing the x-axis in the y direction, and you see we get a matrix that looks like this. It's 1, 0, c, 1. So we get this factor of c in the column that corresponds to the axis we're changing, and in the row that corresponds to the axis that we're tipping it towards. So there's another shear in the xy plane, and that would be shearing the y-axis in the x direction by c. So this would correspond to tipping the y-axis towards the x-axis instead of tipping the x-axis towards the y-axis. And the matrix turns out to follow the same general rule. Along the diagonal, we just get 1s. But then we get a factor c in one of these two positions, and it's in the position, the column for the axis that we're changing, and the row for the direction that we're tipping in. So we get a c in this position right here. Okay. Now, this has to be a linear transformation because I've defined it in terms of a basis, and defining a linear transformation in terms of a basis and then extending it by linearity to all of R2 is guaranteed to give you a linear transformation. That's something that we've seen. So these are the three geometric operations that are expressed really nicely in terms of linear transformations. There's reflection across one of the coordinate axes, there's rotation about the origin, and then there's shearing in one of the coordinate directions. To see how we can use these, let's come up with a linear transformation. Let's come up with a matrix for the linear transformation that performs these geometric operations in this order. So first rotation counterclockwise by pi over 3, then reflection about the y-axis, and then shearing the x-axis in the y direction by -2. So, rotation is going to spin it. Reflection across the y-axis, that reflects horizontally. And shearing the x-axis in the y direction, right, that's going to tip the x-axis towards the y-axis like this. Okay. Well, there are a couple ways we could do this. We could just start with a standard basis and then do these operations and see what outputs we get, and then put all of those outputs into a matrix as columns. But there's a nicer way. We know a matrix for each one of these things individually, and we also know that composing linear transformations corresponds to multiplying their matrices. So we can just write down the matrices for each of these and then multiply them. But we do have to be careful to do the multiplication in the correct order, right? Remember that if we're composing two linear transformations, their matrices multiply this way, so the transformation that you do first turns into the matrix that's on the right. So even though we're doing them in this order, the matrix that corresponds to the rotation will end up on the right of the product, not on the left. So have to be a little careful. So the rotation is what we're doing first, and then we're doing the reflection, and then we're doing the shear. Okay, so let's write the rotation or the matrix for the rotation. Remember, it's cosine minus sine, sine cosine. So cosine pi over 3, sine minus sine pi over 3, sine pi over 3, and cosine pi over 3. For the reflection, remember we put a minus sign on the direction that's being reflected, not the axis that's being reflected across, but the direction that's being reflected. So when we reflect across the y-axis, things are reflecting in the x direction, so it's the x direction that's getting swapped, and so we put a minus sign on the first one in the diagonal. And then for the shear, on the diagonal we just get ones, but since we're shearing the x-axis in the y direction, we need this factor, minus 2, in the column for the axis and the row for the direction we're shearing. So we need a minus 2 in the lower left. And in the upper right, we get a 0. Okay. So now we need to evaluate this matrix product, which is just a matter of doing a bunch of multiplication, or matrix multiplication. This rotation matrix, it's just sines and cosines. So cosine of pi over 3 is a half. Sine of pi over, minus a half. No, plus a half. What am I doing? Sine minus sine of pi over 3 is minus root 3 over 2. Sine pi over 3 is root 3 over 2. Cosine pi over 3 is a half. Okay, and then now we can maybe do this matrix multiplication on the left right away. So we're going to get minus 1 and 2, and then in the second column we're going to get 0 and 1, and then one more matrix multiplication. So let's see, minus a half plus 2 times root 3 over 2, so minus 1 plus 2 root 3 over 2. That's not right. I've forgotten how to multiply matrices. Okay, so upper left corner, first column, first row, we get minus a half. And then here we're going to get 2 plus root 3 over 2. Here we're going to get root 3 over 2. And here we're going to get minus 2 root 3 plus 1 over 2. Okay, I think that's right. Okay, but you can see the idea here is just if you have a bunch of different transformations that you're doing one after the other, you can just multiply their matrices together. And it's pretty quick and painless. Let's look at one more example. Let's find the image of the unit square under this transformation, or the transformation that corresponds to this matrix, and let's express that transformation as a composition of geometric transformations. So when I say the unit square, what I mean is in the xy plane, this is the square that starts at the origin and extends 1 unit in the x and y direction. So it's this square, right? Well, you can see that this square is just made up of, it's sort of bounded by the standard basis vectors, right? Together with sort of their sum here as the diagonal. So we can see what this linear transformation does to this square just by seeing what it does to the standard basis vectors. So let's apply the transformation to these standard basis vectors. Well, E1 times this matrix is just the first column. So first column is minus 1/2 and root 3 over 2. Root 3 over 2 is about 0.8, I think. So minus 1/2 and about 0.8. So, sorry, if this is minus 1, then minus 1/2 is going to be here. 0.8 is going to be about here. So something like this. So if we called this transformation t, then this vector here is t of E1. Okay, t of E2 is just the second column here. And for this one, I think maybe just to get sort of a rough idea of where it actually is, let's get a decimal approximation. So 1 plus square root of 3 divided by 2, and the negative of that. So t of E2 is going to be, first coordinate is about minus 1.36. And second coordinate is minus 1 plus square root of 3 divided by 2. This is going to be 0.366. Okay, so minus 1.36, that's over here, and then 3 points about here. Okay. So this one is t of E2. And remember that this region, this square, started out bounded by these vectors. And what I mean by that is the top of the square is sort of E2, E1, except it's been shifted upwards to the end of E2. And the right-hand side is E2, but it's been shifted rightwards. Right? So to get the resulting shape bounded by these two vectors, we can take t of E2 and sort of slide it to the end of t of E1, and then take t of E1 and slide it to the end of t of E2, and we get this parallelogram. So this parallelogram, right, is the image of this square. So what I mean is, for any vector in this square, when you hit it with the transformation, it ends up inside of this parallelogram. Right? So this parallelogram is the result of the transformation applied to everything in this square. Okay, so let's express this transformation as a composition of geometric transformations. Well, so now we kind of have to use our imagination based on this picture. If we started with this square, how could we end up with this, this result? Well, I mean, it would be nice if t of E1 were actually pointing in the direction of E1. And we can make that happen if we just rotated this. Right? It looks as if this vector that's t of E1, it came from here. It was E1, but we rotated it. So it looks like the last thing that we did was rotation by, well, this vector, right, if this is the result of some rotation, it looks like it's the result of rotating by 2 pi over 3. So 2 pi over 3. I know that just because, right, these are nice values for sine and cosine. So these are the values of cosine and sine for 2 pi over 3. Okay, so that was the last operation. Right? If we sort of undo that, we end up with this parallelogram. Okay, so what operation did we do to the square to get this parallelogram? Well, it looks like a shear. So a shear, how much? It's to know exactly how much this is sheared. Right? You have to sort of carefully think about the length of these vectors. Right? We need to know exactly how much this has been moved up compared to how much it's been moved to the right here compared to how much it's been moved up. So it's a little hard to figure out exactly what shear this is, right? There's some shear here. And we know that it's shearing the y-axis in the x direction because of how this thing is tipped. But it's a little hard to, so this matrix is going to look like, so the y-axis in the x direction. There's going to be some non-zero value here in the upper right, but it's a little hard to know exactly what that should be. Okay. The matrix for the rotation, of course, is cosine 2 pi over 3 minus sine 2 pi over 3, sine 2 pi over 3, and cosine 2 pi over 3. Okay, so there are a couple ways to figure out exactly what the shear is. One nice way is just do this matrix multiplication and set the resulting upper right hand entry equal to this. So let's do it that way. So if we do this matrix multiplication, let's call this C just so it has a name. So if we do this matrix multiplication, we really only need to know what the upper right hand corner is. So that's going to be first row, second column. So, and cosine 2 pi over 3 is minus a half, and minus sine of 2 pi over 3 is minus root 3 over 2. So when we do this multiplication with the first row and the second column, which is going to give us this upper right entry, we get minus c over 2 minus root 3 over 2. Okay. And the matrix that we started with in this upper right hand entry, it was minus 1 plus root 3 over 2. So for these to be the same, that means c has to be 1. So this shear is actually shearing the shearing the y-axis in the x direction by 1, right? Because we got a 1 here. So this linear transformation is first this shear and then this rotation.